Alright, good morning. Today we're going to talk about section 10.3, regression. And let's take a minute and look back in section 10.2, what we did there. In 10.2 we were given paired data, sometimes called bivariate data because it's two variables, perhaps linked by some sort of relationship. And we were given paired data. And given paired data, we can always compute R, the Pearson correlation coefficient, sometimes called the linear correlation coefficient. Alright, and along with R and a given significance level, remember alpha is our significance level, we could then determine if a significant correlation or linear correlation exists. So we can determine whether a correlation exists or not. Given paired data, well, whether there's a correlation or not, we can always draw a scatter plot of variable versus variable. And if I've got a scatter plot that looks something like this, well, we might see that scatter plot is suggesting a strong positive correlation. What we're going to do here is, again, using another operator in our TI-8384 calculator, establish what we call a line of best fit. Line of best fit called the regression line. Alright, now this regression line equation will be computed by the TI-8384 calculator, and it's just note that it's the line that's geometrically as close, that's closest to all the given data values. Let me write that down. Regression line is the closest line that can be drawn to all given data values. Okay? Alright. The TI-8384 will calculate regression line equation, and it gives it to us in a particular form we got to get comfortable with, and more about that later today. Okay? Alright, note, and the big motivation here is we can use, under certain circumstances, we can use the regression line equation to predict values of variables for which we have no information, but there's a big proviso if, and that's only if, a correlation can be established. So let me write that down. We will use the regression line equation, and the TI calculator gives us our regression line equation in the form a plus bx, and I think we can agree that this is a line equation similar to the slope-intercept form y equals mx plus b, but the TI will give us the regression line equation in this form, y equals a plus bx, so certainly a line equation. Alright, write that down. This is in the form y equals a plus bx. Alright, we can use the regression line equation to predict values of variables for which we have no information given, and a very useful tool indeed. Alright, let me put that proviso down here. If a correlation can be established. Okay, we use the regression line equation to predict values of variables if a correlation can be established, as in section 10.2. I want to jump right to an example. I want to do one out of the homework list. This is going to be number 13 in page 529. If you look at this data, well, you'll quickly see that it's the same data given in number 13 in section 10.2, where we had the measured lemon imports from Mexico in metric tons and the crash fatality rate per 100,000 in the United States. Let me quickly copy down these values again. Same values as we used in the last online lecture, 230, 265, 358, 480, 530, and 15.9, 15.7, 15.4, 15.3, and 14.9. Alright, I'm going to break this up into two parts. Right, kind of changing what the book says about number 13 in section 10.3. First thing I'll say is determine in part A if a correlation exists between these two variables at alpha at a significance level of 0.05. Alright, nothing new there. We did part A in section 10.2. Now part B is going to be new here. I'll say find equation, let's see, use data, I'll say just, I'll kind of shorten it a little, I'll say predict the crash fatality rate in a year which 500 metric tons of lemons are imported into the U.S. Okay, to do part B, we're going to establish a regression line equation and use that line equation to predict crash rate at a given lemon import level. Alright, so this is a problem. We might see something like this on homework or our last test. Part A, let's talk about Part A first. Well, Part A, nothing new. We already did Part A in section 10.2, did we not? Again, we used the using the Lin-Reg t-test operator. We established a correlation coefficient of negative 0.959, alright, which might suggest a strong linear correlation. We established critical values of plus or minus negative 0.87 or plus or minus 0.878. Alright. And from those critical values and from this value of R, we indeed established a significant negative linear correlation existed between these two variables. Okay? Well, that means as your lemon imports go up in metric tons, your crash rate goes down in rate per 100,000, and who knows why? Well, again, as statisticians, we don't explain the why, we just explain whether a correlation exists. Okay? Alright, let's look at part B now. We want to predict the crash fatality rate in a year which 500 metric tons of lemons are imported. Well, if you look at the data, well, we don't have an input level of 500 metric tons to predict an output of a crash rate, right? To predict a needed crash rate. Alright, so we're going to need another tool to establish these prediction capabilities. Alright, what I'm going to do is first and foremost, I'll note a correlation exists right, as we established in Part A. And if a correlation exists, then we can use the regression line equation to predict the value of a certain variable that we have no information about. Okay? Alright, so we want to establish the the regression line equation. Right? To compute the regression line equation, we're going to use the linreg t-test command, just like we did to compute R. Right? It's going to be in the same screen output where we found R in section 10.2. Well, the first thing we're going to do is clear out all the old data from L1 and L2. L1 and L2 are by default the lists used in that linreg t-test command. Alright, so clear out the old data in L1, L2. Again, you know how to do that. Hit stat, edit, clear out all the old data, put in all the new data, and in L1 I would ask us to put the lemon import values as specified above, and in L2 put the corresponding crash rate data values. Right? And enter in the new data. Right? Alright, once that's done, we still want the regression line equation. Right? So once you've entered the new data, again we'll hit stat, tests on our calculator, again scroll down to linreg t-test. Alright, for the X list, well, we'll use L1, that's the default. The Y list, that's going to be the crash rate values, L2. Skip the next 3 lines. Skip the next 3 lines, the frequency, the beta and rho, and the reg EQ. Skip those and scroll right down to calculate, and it entered twice. And you'll see an output screen that we should be familiar with from section 10.2. It's the linreg t-test output. You'll notice at the very top of the screen it says y equals a plus bx. Okay, that's the form that the TI-83 gives us our regression line equation in. Right? And if we scroll down, you'll see an a value of 16.49 and a b value of minus 0.00282, we'll call it. And R, of course, is down the line here in this output screen, but we know that already. It's minus 0.959. Alright, so I'm going to grab these A and B values, and these are the A and B values I'm going to plug in for my regression line equation. Couldn't be simpler, right? So my regression line equation for the data above, the lemon import versus the crash rate data, is y equals 16.49 for A, plus B is minus 0.00282 for B times X. Now remember, our X variables are going to be the lemon imports, the lemon import level, and the Y variable is our crash rate, fatality crash rate. Okay? Alright, so a very powerful tool here. And since we have already established that a correlation exists between these two variables, we can use the regression line equation to predict Y values or crash rate values at any given lemon import level. All right, let me write that down. We'll use this regression line to predict y values, which were our crash rate values, for a given x value. Well, x here was our lemon import value. Alright? So in this problem specifically, we were asked to predict the crash rate, the car crash fatality rate, at a level of 500 metric ton import of lemons, right? So I'll say this, with lemon imports at 500 metric tons, right, I can say my car crash rate can be expressed according to this equation. I simply plug in 500 for x in my regression line equation and grind it out on the calculator. So y equals 16.49 plus minus 0.00282 times 500, and y equals 15.08, and remember that's in fatalities per 100,000. Those were the units given in the original table. Alright, so that's what regression line is all about. Predicting variables for at points which we have no specific information. Okay? Alright. We get a fresh screen. Let's make a couple notes here before we go on to another example. Again, the TI likes to give us our regression line equations in this particular format: y equals a plus bx, and again analogous to y equals mx plus b, a line equation in slope-intercept form in a first algebra course. By convention, the x variable is referred to as the predictor variable. There's other names depending on the textbook that you read. I like to call it a predictor variable. It's what you're using to predict a given needed value. The y variable. Well, again, the names of this variable change depending on which text you're using. I like to call it a predicted or response variable. Alright, so the convention in the TI-8384 is to use x, your x list, your L1 list for the predictor variable. Again, that's by convention. And then to use list L2 for the predicted or response variable. Okay? Alright. Let's try another example here. I'll say, what if no correlation exists? Again, we can only use the regression line when we have specified that a correlation does exist. And I'm going to give it as an example of that the shoe length versus the height data we talked about in section 10.2 online class. And this was in the chapter problem, as we recall. If you want to look at it in your book again on page 495. All right, let me briefly copy down that data. We've got our shoe length in centimeters and a corresponding height in centimeters for 5 different people. And let me copy them down briefly here. Same data as we used last time in section 10.2. 6. And the corresponding heights, again, these are in centimeters, of course. Okay. And again, I'll break this up into this example into a part A and part B. And I'll say determine if a correlation between these variables exists. Determine if correlation exists at alpha equals 0.05 significance level, and then I'll say predict the height of a person with a 30 centimeter shoe length. Alright, nothing new about part A. We've already done part A last time, if you recall. At alpha equals 0.05, again, we're looking at part A, we found the critical values from table A6 in the back of the book were plus or minus 0.878. We have 5 data points at the 0.05 significance level. We had an R value of positive 0.591. A relationship that may be a weak one here. Certainly 0.591 does not overcome the bar of positive 0.878. So you'll recall in part A and last section we determined that no correlation exists. Between these two variables. Okay. Part B. Predict the height. Well, we can only use regression line if a correlation exists. Can only use regression line if a correlation, positive or negative, exists. So what are we going to do here? Because we know that no correlation exists. Alright. Well, to predict a y value or a predicted variable value, here we will use y bar, again, if no correlation exists. And of course, as you might expect, y bar is nothing more than the average or the mean of all the y or predicted variable values. Alright, so here, to predict the height at shoe length equals 30 centimeters, right? Let me check my notes here. At shoe length equals 30 centimeters, we use y bar equals the mean or average of all heights. Alright, so all you got to do here, you can't use the regression line, you just find the height of all these people indicated in the table, and it turns out to be 177.3 in centimeters. Alright, so the long and short of it is no correlation. Just use the mean of all your predicted or response variable values. Alright, long and short of it is to predict. Alright, if correlation exists, we'll use regression line, and if not, if no correlation exists, use the mean of all the response or predicted variable values. Alright, so we've done an example of when to use the regression line and how to use it, and an example of when not to use the regression line equation. So we'll call it a day for section 10.3, and this concludes section 10.3.